Hello and welcome back to another IB Math speedrun with me, Vince. In this speedrun, we'll be going through the roots of a complex number in polar form. So let's jump right in. So what do we need to know about the roots of a complex number? So just like the powers of a complex number, the roots of a complex number, at least in polar form, is equal to, say we have a complex number, z equals r cis theta. Well, the roots of this, the n, will be equal to r to the n cis theta over n. Except that there's a little catch here. I mean, this all looks pretty obvious, except the problem is that there are actually multiple roots for each complex number. Since, remember, this number is really theta plus 2k pi, because all of these numbers would be equal, where k is equal to real number. So this is actually equal to theta plus 2k pi over n, with 2k pi also being over n. So this produces multiple solutions that we need to account for. With that being said, we can now jump into some questions. So first is, given the complex number w is not equal to -1, is a solution of z cubed plus 1 is equal to 0, show that, first, w squared, I mean it's really omega squared, but I don't have the omega symbol. The complex conjugate of w squared minus the complex conjugate of w plus 1 is equal to 0. And finally, hence calculate omega to the 2019 plus omega to the 2020 minus omega to the 2021 plus omega to the 2022. So first, w, so we have omega is a solution of z cubed plus 1 equals 0. Okay. So, so then, therefore, omega cubed is equal to -1. So, and omega is not equal to -1. So what we have here is a complex number, say r cosine theta, or just let's just do r to the e pi, r to the ei theta, or this is actually r cubed to the e to the 3i theta is equal to negative e to the I, no, it's just equal to e to the I pi. So we have r cubed is equal to 1, and theta is equal to, so therefore r is equal to plus or minus 1. And 3 theta is equal to pi, so theta is equal to pi over 3. So our complex number will look like e to the I pi over 3. So first we need to show that it's a solution to this equation, so let's do that. So we have this squared minus itself plus 1. I think that's plus 1? Plus 1 equals 0. So over here we have e to the 2i to I to the 2 pi over 3 minus e to the I pi over 3 plus 1 is equal to 0. So we need to prove this, and we can do this by converting this back into form. So we have cosine 2 pi over 3 plus I sine 2 pi over 3 minus cosine pi over 3 minus I sine pi over 3 plus 1 is equal to 0. So what can we get from this? Well, we know that I sine 2 pi over 3 and I sine pi over 3 are equal, so we can cancel these out. So cosine 2 pi over 3 is equal to negative 1/2 minus cosine pi over 3 negative 1/2 plus 1 is equal to 0. So of course it is a solution. And next, because this number is a solution, of course its conjugate also needs to be a solution to this equation. So it follows. And so finally, we need to calculate this sum. So w to the 2019 plus w to the 2020 minus w to the 2021 plus w to the 2022. Okay. So what we can do here is we can factorize this. And so we have w cubed. Well, it's 2019 is divisible by 3, right? So we can factor that one out. So 2019 divided by 3 is 673. And since we know that omega is a solution of z cubed is negative 1, so this will be negative 1 to the 673. In other words, this will be equal to negative 1. And then we can factor this into plus omega to the 2020 times 1 minus omega plus omega squared. So we can see it matches this formula over here. And so we know that since omega is a solution, this will be equal to 0. So this entire thing is simply equal to negative 1. Okay, so on to the next question. And so the next question is find all the complex numbers in Euler's form. So we have this fourth root of negative 625, and we need to find this in Euler's form. So how can we express negative 625 in Euler's form? Well, negative 625 is equal to negative 625, or 625 e to the I pi. So if we take the fourth root of this is the fourth root of 625 times e to the I pi over 4. So fourth root of 625 is 5, so this is simply 5 e to the I pi over 4. So that is the fourth root of 625 expressed in Euler's form. Oh, except that technically we have to add plus, and then we have to add k over 2, since remember this is e to the I pi plus 2k pi. So we also have to divide 2k pi by 4. So this is e to the I pi over 4 plus k over 2. Yeah, so 5 e to the I pi I pi over 4 plus k over 2. So pi times 1 over 4. Next, we need to get the sixth root of negative 1/2 plus root 3 over 2i. So we can express this as just e to the I pi over 2 pi over 3. So this is we're trying to get the sixth root of e to the I, and then this is actually pi times 2 over 3 plus 2k, which is equal to e to the I pi times 2 over 12 plus 1/3 k plus k over 3. So this should be the new number. Unless, sorry, no, I've made an error. Sorry, 2 divided by, sorry, this is 1/9, not 2/3. So yeah, this is correct. And then finally, we have the last question where we have the complex number, which is negative 4 root 2 plus 4 root 2i. So we need to first write it in Euler's form. Show the real part of the complex number 6 root z. So root 6z is equal to square root 2 plus 4 divided by 2, and then find the exact form of the imaginary part. So do we just assume that, okay, I guess. So how can we write this in Euler's form? Well, this is going to be e to the I. We have negative cosine, so this is going to be 3 pi over 4 times, is it 8? I think it's 8e I to the pi 3 over 4, yeah. So, next we need to find the real part of the 6th root of this number. So, and I think this means we ignore the plus k over here. So we have 6th root is the 6th root of 8, which is equal to the square root 2, times e to the I 3 pi over 4. So 6th root, so this is e to the I pi over 8. So we can find the real part by making this square root 2 cis pi over 8, which is equal to square root 2. So the real part would be square root 2 cosine pi over 8. And well, what's cosine pi over 8? We haven't really discussed half angle formulae, so we should probably do that now, because we can find this by substituting it back into the cosine equation. So if we have cosine 2 theta is equal to 2 cosine squared theta minus 1. This is identity too. So we can say that cosine pi over 4 is equal to 2 cosine squared pi over 8 minus 1. So cosine pi over 4 is root 2 over 2. So root 2 over 2 plus 1 divided by 2 is equal to cosine squared pi over 8. Let's see if we can simplify this a little. This is root 2 plus 2 over 4. And so we can square root all of that to get cosine pi over 8. And so we can multiply this by root 2. So we have root 2. So we have the square root of 2 root 2 plus 4 over 4. What do we need to prove it equals? Oh, no, wait, no, this should be 4. No, what am I doing? This should be 4. It's just that I didn't see that they removed the square root sign. So this bottom part is only equal to 2. So this is the real part. And finally, find the exact form of the imaginary part. We can use the same trick to find sine pi over 8. I mean, of course, there are other ways to do it, but we could just use the same trick. So we have cosine pi over 4 is equal to 1 minus 2 sine squared pi over 8. So we know this is square root 2 over 2 plus minus 1. So we have 1 minus square root 2 over 2 is equal to 2. All over 2 is equal to sine squared pi over 8. So we have here 2 minus root 2 over 4, the square root of 2 minus root 2 over 4. And then now we need to multiply root 2 to it. So this is square root 2 times 2 square root 2 over 4i, which is equal to square root 2 root 2 minus 2 over 4. In other words, it's 2 root 2 minus 2 over 2i. This is the exact form of the imaginary part. So let's just check this. So square root 2 root 2, square root 2 root 2 minus 2 divided by 2. So yeah, this is approximately equal to the correct answer. So that was all for the speedrun. I hope you enjoyed, and I hope to see you in the next one. See you then.